Okay, let's begin. Let's start off with the problem. So last time we learned about what a sequence was. It was just an ordered list, some sort of list in a definite order. You could also think of it as a function whose inputs are the positive integers. So pretty much I have a list here whose input is given by that formula, which means this describes a list here by, well, 1 over 1 to the 1, and the next guy is going to be 2 factorial over 2 to the 2, the next guy is going to be 3 factorial over 3 to the 3, etc. Now, okay, so first question, does everyone know what this symbol means? Yes. All right, so let's talk about that first. So this is a new definition. You might have seen it in some other math classes before, like if you've done statistics or probability before, chances are you've seen this guy. If not, well, now you're going to know. So this is something that's called a factorial. So the symbol is n with an exclamation point. So it's not n, it's n factorial. So it's not like you're shouting. It actually means n factorial. Right? Now what that is actually defined as is n is considered a positive integer, and or 0, could be non-negative, and is considered to be the product of all integers up to n. So from 1 times 2 times 3 times n minus 1 all the way to n. With 0 factorial being considered as 1 by convention. So, for example, if I write this down, it's 5 factorial. And what that means is I'm taking 1 times 2 times 3 times 4 times 5, which will get 120. So that's just another way of writing 120. Right? So that's 5 factorial. That's called a factorial. There are many things that this number can do for you. For example, it's the number of ways to arrange n objects. This is probably how you would have seen it in like probability or statistics. So 5 factorial, it also represents the number of ways you can take 5 things and rearrange them in a list and just change the order and get a different list. You can do that in 120 ways. So that's what that guy is. So this is n factorial. And this is just n raised to the nth power exponentiation. We kind of know what that means. So we have a list like this, right? So it's it goes from, well, 1, then it goes, 2 factorial is 2, by that definition, 2 over 4, then it goes to 6 over 9, etc. Okay. So that's the list. And so now I'm asking you, does that actually converge? And remember, what did it mean to converge? What did that mean? Like I asked some questions on convergence of sequences on this quiz, so hopefully.
The limit as n approaches infinity.
Right, you look at the limit as n approaches infinity. Sometimes you can leave this off because when you're talking about sequences, it's always as you approach infinity. We mentioned that last time. Of a n, and that means you get L, where L is a real number. And if no such L exists, we say a n diverges. So to say something converges means I take the limit as n approaches infinity and I get some meaningful answer. Meaningful in the sense that it's a real number. If I get infinity or a DNE or something bouncing up and down, then I say it diverges. So does this actually converge? Now hopefully we fully understand this question. Ideas? Yeah.
Okay, I thought of it, like, I can't really put it into words necessarily, but like, I thought of n factorial as like n times n minus 1 times n minus 2. And then n to the n is just n times n times n times n. And the bottom is like more stronger, I'd say. So as that approaches infinity, the whole thing would approach 0.
So, all right, so we want to take the limit of a n, which in fact means the limit of n factorial over n to the n. So you just thought of n factorial as by the definition. You did it the other way, but it's it's fine. N times n minus 1 times n minus 2 times going all the way down to 3 times 2 times 1. Okay, so that's what the top looks like. And the bottom is, well, it's just n times n times n times, all the way down to n times n times n. Now, we saw that limits actually distribute across products. So, we can actually think of this like that. Now, this guy here is of course going to go to 1, but eventually these guys actually get smaller as you move down. And if you look at like the last guy, 1 over n, as n is approaching infinity, well, that guy's going to go to 0. So I'm just going to ultimately have a bunch of things multiplying to give me, and in the list, there's a 0 in the list, so that kind of tells you the answer is, well, 0. So this does converge. Yes. An converges to 0. Now this actually reminds you, hopefully it reminds you, of something that you saw in Calculus 1, where we had that list of things. And in Calculus 1, we never saw the factorial, but now we're going to do a lot with factorials. So about the magnitude of certain functions, knowing that, for example, a logarithm is smaller than a polynomial, which is smaller than an exponential, which is smaller than a factorial. Now, it turns out that you can actually define this function on all real numbers, not just integers. That's a whole other math class, though, like a couple levels beyond this one, so we're not even going to worry about that. But in general, you could actually define a function using something called a gamma function to define it for all real numbers. But factorials, especially, are bigger than exponentials, and larger than factorials are things that look like that, x to the x, right? So what you'll notice is in this limit, I had 2 of these guys competing, and remember what this thing means. This thing means, say, x to the a is much larger than log to the base a as x goes to infinity, which means logs grow slower than polynomials, which grow slower than exponentials, which grow slower than factorials, which grow slower than the variable exponential. And the idea is, as your x is going off to infinity, the guys on the right are going to be larger than guys on the left by so much that the guys on the left might as well be 0. They might as well not even try. They just grow way too slow. They're going to be way too small by comparison. So essentially, what you have here is a bottom-heavy limit. The guy on the bottom is huge compared to the guy on the top, which is to the left of that. So you have a huge denominator, a small numerator. So you get a fraction that approaches 0. But this is just a nicer way to, if you want to see how it's happening, that's how you can look at it. So it reminds you of that list, and this list was important for limits, and hence it's important here. Another thing that you should remember about limits, I'm going to expect you to remember something called L'Hopital's rule. So, basically, if you have a limit, of course there were some continuity requirements and differentiability requirements and all that, but it's going to be clear when this can work out. If you have a limit of a ratio and it approaches 0 over 0 or infinity over infinity, plus or minus, then you'd be able to compute that limit by computing a different limit. Which limit?
derivative of
prime over d prime. You can differentiate the top and bottom separately, and the original limit will be equal to that limit, provided the limit on the right exists.
It's like one hand.
This is called L'Hopital's rule, and these guys are two examples of forms that we call indeterminate forms. The others were 1 to the infinity, infinity to the 0, 0 to the 0, 0 times infinity, infinity minus infinity. I always forget one of these. Okay, so 1, 2, 3, 4, 5, 6, 7. I think that's all. Right, so these are all the indeterminate forms. When you get them inside of limits, you should know that you can't assume that you know the answer to one of these. You need something else. Odds are, if you approach any one of these situations in a limit, which I think on the bonus you would have actually approached some of these situations. If you approach any of these situations in a limit, what you want to do is use algebra to finagle them to look like one of these forms, which in this case what you can do is you can log both sides, allows you to bring the power down and get a multiplication, and then you take one part, take its reciprocal and move it into the denominator. That will give you a fraction. Very similar strategy will work on these two. Here it's a multiplication, take the reciprocal of 1, move it to the denominator, you'll get one of these forms. Infinity minus infinity, you're either going to factor or combine terms to get one big fraction, and hopefully you can transform any of these forms to any of those forms. Expect you to remember things like that. So if you have, for example, an where it's given by an equals ln n over, say, e to the n, or whatever. You want to know if that converges or what it converges to. Well, one way you can do that is to just recognize from this list that the exponential is going to be larger than the logarithm, and so that obviously would converge to 0. So you can do this by the list. Or what you can do is you can notice that if I look at ln n over e to the n, this guy goes to, well, infinity over infinity. And so I can apply the L'Hopital rule. So the limit of this is going to be, you can differentiate the top, which is 1 over n, differentiate the bottom, which is e to the n. And so this is just the limit of 1 over n e to the n, which clearly now approaches 0. So you get two ways you can approach the answer. One way might be easier than another. But yeah, so a sequence like this will actually approach 0. A couple ways you can get to that. L'Hopital's rule. So you should remember this list. You should remember about limits in general, all the properties. You should remember L'Hopital's rule. You should remember, what else did you learn? Limits. Squeeze theorem. So all of these you went over in Calc 1, so I'm not trying to teach you anything new here, I'm just trying to jog your memory a little bit. Also, remember, squeeze theorem. So that might be applied here. So that's the theorem that says if you have, for example, say an is less than or equal to bn less than or equal to cn, and you know that an approaches some number L, and at the same time cn approaches some number L, then you can conclude that your bn must approach some number L. The idea is you can take the limit of everybody here, and the left side and the right side go to the same number L, so the limit of the inside must be greater than or equal to L, but at the same time less than or equal to L. Well, the only way to reconcile that is for it to actually be L. So the limit in the middle have to be L. So you can also apply that. So if I have something like, example, if I have an equals the sine of n over n, what I can do is I can note that my sine n is always going to be between those two, which means I can divide everyone by n. Means I can take the limit of everybody. This guy would approach 0. And that guy would approach 0. So it actually tells you that sine n over n would approach 0. Right? And you can say vice versa. That's something else you have to remember when it comes to convergence. Anyway, knowing what, when sequences converge is going to be very important. Why are they important? Well, for the next thing that we're going to do. So, the main attraction for this phase of the class are objects called series. And pretty much, we only care about sequences as far as they will help us with series. So sequences, it's an important topic in its own right, but we only cover enough for them to help us with series. So that's the next major topic, and we're going to spend a while on this topic. Let's talk about series. So, let's do with some motivation here. So, 450 BC, right? There was this dude by the name of Zeno. Came up with a bunch of paradoxes, or what he thought was paradoxes. There were about 40 of them. Most of them were lost. Some of them were recounted by Plato and Aristotle in their writings, but the original were lost. Anyway, this dude Zeno fancied himself a philosopher. Most people did back then. You know, that was kind of the main game. You know, you go to the bar and say, "I'm a philosopher. What's up?" Right? Well, either that or it's like, "I'm a military general. Just conquer that." You know, like those are the only two games. You know, you're either one of those two things or a farmer. So we're in a period of time where philosophy was all the rage, right? So these guys always come up with these brain teasers and things trying to get over on their friends. Anyway, this dude named Zeno came up with a bunch of paradoxes. One of them was called the dichotomy paradox. So here's what the dichotomy paradox says. It basically says, in order to achieve something, you first have to achieve a part of that thing, right? To get the whole job done, you have to first get half the job done, and so on and so forth. So he mentioned something like, to cover a distance, you must first cover half that distance. Right? So now he's like, consider a mile. Right? Like 1 mile. How can you travel 1 mile? So he goes and he's like, well, in order to travel a mile, so let's say I'm here and I want to travel a mile, walking. There comes a point where I've traveled half a mile, right? Before I can travel a whole mile, I have to travel half a mile. So now I'm at the point where I've traveled half a mile. How much more do I have to travel to get to a mile? Well, a half a mile. So I have to travel now half a mile. But before I get to a half a mile, I have to travel a half of the half a mile, right? So I travel a quarter mile. Now I have a quarter of a mile left. Before I can travel a quarter of a mile, there must come a point where I travel a half of the quarter of a mile, an eighth of a mile, and so on and so forth. So he is like, okay, in order to travel a mile, you first have to travel a distance of a half a mile. Then you have to travel a distance of a quarter of a mile. Then you have to travel a distance of an eighth of a mile. Then a 16th of a mile. Then, so his conclusion is, how does anyone ever actually travel a mile? Right? So he thought he was being very smart. And he's like, you have an infinite addition of things here. There's no way that that's actually a number. right? How does anyone ever travel a mile? And all the philosophers are arguing about how you can travel a mile, and reality is fake, and no one actually, right? So all that stuff came into play, right? So he came up with a philosophy that ended up in the real world, you're traveling a mile, but in this philosophy, it equated to kind of adding up this infinite sum. Does this actually make sense? Was the question. Does this make sense? Now, of course, the obvious answer is it has to make sense because people travel miles all the time, right? It must be that this thing, this expression that you wrote down, it has to have some meaning. It can't just be meaningless, or it can't just be, well, we're adding up a bunch of positive things, so it has to go off to infinity. There's no way that goes off to infinity. There's no way that it doesn't have meaning. How do I know? Because I traveled several miles to get here today. So if I had to achieve this in order to travel, and it never actually ends anywhere, I would have never made it here. So there must be a meaning to quantities like this. So this brought up the idea, way back in the 400 BCs, of infinite sums. So, and we're thinking about this for a really long time, okay? So, we have the idea of an infinite sum. Can we add up an infinite number of things and somehow get a meaningful answer? Now, of course, the calculus students are going to scoff at this because we know something called the integral. To achieve that, we have to add up an infinite number of things, right? That's what a Riemann sum was for the definite integral, right? We added up an infinite number of areas, and we came up with an answer. But back in the day, it wasn't so clear. It wasn't clear what it meant to add up an infinite number of things. So what series does is it kind of gets to the heart of this. So another way of talking about infinite sums, we call them infinite series. So a series is just another word for sum, right? Kind of like how a derivative is another word for slope. So when you want to talk about slope, like in general, the essence of slope, what is that? You say derivative, right? So that's kind of like what a slope means, right? When you talk about a sum, I'm not just talking about 1 plus 2 plus 7, right? What does it mean to really add something? Like to add in all contexts, what does it mean? When you want to think of that idea, you use the phrase series. I'm not talking about your grandmother's addition, I'm talking about real bona fide addition. Like what does it mean to add something together, okay? And so we have the idea of an infinite series. And so how do we make this mathematical? And how do we actually get to the point where we can conclude that this would actually add up to 1, which makes a lot of sense that it should add up to 1, based on Zeno's paradox. So we came up with a definition here, and we defined something called a series. And a series is the sum of the terms of a sequence. So here's how our sequences are going to come into play. Define a list of numbers, but you're not just going to define them in any random way. You're going to think of them particularly as a sequence. Meaning, in the background, you're thinking of this guy as an A1, and that's an A2, and that's an A3, and so on and so forth, right? And that little spark of imagination is actually going to take us very, very far. So it's just the sum of the terms of a sequence. So a sequence is just a list in a definite order. You get a series when you start adding up the things in that list. So the notation here, it's notation we've seen before, the sigma notation. Write this. So we can say like n goes from 1 to infinity. And you can write the expression here like an, right? And what that basically means is you're gonna take the list, of course we know how we generate the list, plug in 1 into the formula, get an output, plug in 2, then plug in 3, then plug in 4. You'll have a list of things, but what the series does is it now adds them together, right? So we had that list from before, but now we're going on to adding the members of the list. Now, notice here that this is going to continue forever. Why? Because this goes off to infinity. So like with the sequence notation, this here tells you the starting point. This here tells you the ending point. Right. When I write that expression, I'm talking about a series. So this guy here is an infinite series. Now, you can have a finite series, so I could say something like n goes from 1 up to big N of a little n, and I can say, oh, that's a1 plus a2 plus a3, and that one dot 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 eventually stops at a number. This one here is called a finite series. Now, finite series, uninteresting. We're not going to care about them at all. Right? Given enough time, you know, a preschooler can deal with finite series. You teach them how to add little rocks in this. Go at it, little kid. Okay, so you can add up a finite number of things. It's not a big deal. When you start adding up an infinite number of things, things start to get strange. And now you have to get a little bit more sophisticated with how you're thinking of adding things. So our attention is going to be focused here for the next few weeks. 2 to 3 weeks. Our attention. We are going to talk about infinite series. We're going to talk about knowing whether or not they make sense. How can we figure out if they add up to anything? Can we figure out what they add up to? And we're going to look at some important consequences of these guys, particularly in the calculus context. What does this guy mean? But it's worth mentioning that series, yes, you use them for Riemann sums. Yes, we're studying them in Calc 2. But series is a whole topic altogether by itself. It goes into areas of math beyond calculus. It goes into areas of computer science beyond calculus. It goes into areas of engineering beyond calculus. It is the essence of what it means to add stuff up. It's not confined to calculus at all. It is a general thing that we're going to look at. Now, we do use it in calculus, but it's used elsewhere as well. It's a very important idea to get a handle on, the idea of a series. And a lot more things run on series than you might think. So your TI-89, which you love so much, is almost all about series. Like your calculator computes things using series, right? So a lot of times your computer or your calculator is computing anything numerical. It's doing it in a series way. And so what we're going to do now, we're going to show you what your calculator is thinking when you ask it to compute something. And we're going to learn how to compute things ourselves. So yeah, so that's a series. That's what a series is. It's just a fancy name for a sum. Now, when the sum starts to have infinite length, things start to get a little bit complicated, and we want to know how to deal with that complication. So, let's many directions I can go in. What do I want to talk about? How do you make sense of something like this? Right? So, here's the idea. Suppose we wanted to compute a finite sum. What is a way that we can do that? Say 1 plus 2 plus 3 plus 4 plus 5. Here's one way in which we could do that. Yes, we could add them all up together, but let's go back to the preschoolers. How will a preschooler add this up? Well, 2 at a time, actually. They'll start with, well, 1 plus 2, and they'll get an answer, and then they'll get, okay, plus 3, and then they'll get an answer, and then plus 4, and then that's how they'll do it, right? So, in other words, what you would do is you would consider what's called partial sum. So, you'll first consider let's say S1, which is called 1, right? That's the first guy. Then you'll talk about the second guy, right? Which is 1 plus 2, and you'll end up with 3. And then you'll talk about the third sum, the sum of the first 3, right? That adds up to 6, and then, okay, you go to the sum of the first 4, and that's 1 plus 2 plus 3 plus 4. And so that adds up to 10, and then you go to the sum of the first 5. 1 plus 2 plus 3 plus 4 plus 5, and you get 15, right? So these guys are called partial sums. P-A-R-T-I-A-L sums. One thing I want you to notice is that I was labeling them very suggestively. They generate a sequence. It's called the sequence of partial sums, because you know how math people are naming things. So, you want to add something, one way you can do it is add it in pieces, and then actually look at what the pieces are doing. So in this case, if I were to look at the sequence of partial sums for this particular example, so here, what I could realize that I could create a sequence, Sn, and it is going to be a list, 1, then 3, then 6, then 10, then 15. And the idea is, what does it mean to actually add up everything? Well, it means you kind of follow this list until you get to the last guy. That last guy is going to be your answer. In other words, you have a sequence, and what that sequence is describing, what is the rule, the definite order of this list, is it just adds the next term, then the next term, the next term. And you create a list by adding successive terms. And then just look for the long run, where does the list end up? And in this case, it ended up at 15, and 15 is actually the answer. 1 plus 2 plus 3 plus 4 plus 5 is 15. That is the answer to this sum. So now you apply this rule in general. We define the definition. We say a series equals S, where S is some number, if the limit of Sn equals S, where Sn is the sequence of its partial sums. So the idea is the following. For an infinite series, the sequence of partial sums is going to generate an infinite list. If the answer to your sum is the last guy, what do you want to do? You go to the last guy. But what does that mean? You just go off to infinity. You just go and you just keep going. And the hope is, eventually, the sequence is going to settle. It's going to repeat some number after a while, as far as the limit is concerned. And that's going to be your answer for the sum. So that's how we're going to define addition. And we say the series converges to S, right? And we use the language of converges because that was the language we used when the sequence converges, right? So we create a sequence of partial sums of a series and watch where it ends up, because where it ends up is the answer to the sum. And we say, if it ends up somewhere meaningful, like at an answer, like 5 or pi or 17, we say, oh, that infinite sum has a meaningful answer. The answer is 17. And we can say the series converges to 17. If I were to add up all the numbers in this list, 17 would be the answer, right? So this is basically the definition of what it means to actually add up an infinite number of things. Generate a sequence of partial sums, find what it converges to. That is the answer for your series. Now, you might say, well, how do we know that makes sense? Well, hold on. We'll get to a point where it's going to make sense, because we're going to it turns out that that coincides nicely with reality. Similarly, if no such S exists, i.e. Sn diverges, we say the series diverges. So, you have a series, what it is, it's just adding the members of some list. It converges, it adds up to some meaningful number, so meaning some real number, and it diverges if it doesn't add up to anything, right? So if it goes off to infinity, or you have in this case where you're bouncing up and down, we say it diverges. Let's look at an example. Let's see if this way of looking at the world actually makes sense with Zeno's paradox. Let's actually answer Zeno's paradox. Couple millennia too late, but better late than never, right? Let's say you wanted to add up all of those numbers. How would you actually go about doing it? Well, one way we could do this is create a sequence of partial sums. So, the first guy, the sum of the first guy. That's a half. That's the first partial sum. And you take the sum of the first two guys. So that's going to be a half plus a quarter. That's the second partial sum. Then three guys, we're going to have a half plus a quarter plus an eighth. That is the third partial sum. And then we're going to have a half plus a quarter plus an eighth. That is the plus 16th. That's the fourth partial sum. This idea is going to go down all the way to Sn, which is a half plus a quarter plus an eighth. Does anyone recognize a pattern that I can talk about the general term here? Like if I had to say this in terms of n?
N over 2. Well, no, 1 times 2.
1 over n.
How can I describe this as a formula? Like what would the nth guy look like?
2.
Yeah? 1 over 2n?
2 to the n.
Does that make sense? The first, if I plug in n equals 1, I would get a half. Plug in n equals 2, I would get a quarter. Plug in n equals 3, I get a 6. So no. Yeah.
N plus 1 over 2n.
And plus 1 over 2n. So if I plug in n equals 1, I would just get 1. So no. Yeah.
Would it just be 1 over 2 to the n power?
1 over 2 to the nth power. Right? The numerator is always 1, so I'm going to guess that's 1. What's happening to the denominator? I keep doubling it. So 2, then 2 times 2, then 2 times 2 times 2, then 2. Right? So this is 1 over 2 to the 1, 2 to the square, 2 to the third, all the way over. So the general term looks like this: 1 over 2 to the n. Now the question is, can I talk about what this is as a formula so that I can find its limit? Because me having it as a list isn't very convenient. So one way we can go about this, we can actually try to come up with some formula here. Here, creating common denominator, this would be 3 over 4. If I take 3 over 4 plus an eighth, that is the same as 6 over 8 plus an eighth, that's 7 over 8. If I take 7 over 8 plus the 16th, that's the same as 14 over 16 plus 1 over 16, 15 over 16. Do you think you can, in the same way that you came up with an idea for what the last guy would look like, can you come up with an idea, a formula that will give us all of these numbers? Well, we already know what the denominators behave like, right? 2, then 4, then 8, then 16. It's exactly the same as. So the denominator is going to be 2 to a power, right? So the first one is 2 to the 1 power. Then the second one is 2 to the 2 power. Then the third one is 2 to the third power. And then the fourth one is 2 to the fourth power, etc. What does the numerator look like? Yeah?
2n plus 1.
Well, is this 2 times 1 plus 1? No, that would not give you 1. Yes?
2n minus 1 would do the trick?
2n minus 1. If I plug in 1 for that, I would get 1. If I plug in 2 for that, I would get 4 minus 1. That gives me 3.
Wait.
Oh, there's hope. If I plug in 3 for that, 6 minus 1 is 5. So
Whatever it is. Like, could raise the power.
yeah.
Okay, how about 2 to the nth power minus 1? Not n minus 1, but 2 to the nth power down, just minus 1.
Yeah, like notice that the numerator is always just 1 less than the denominator, right? 1 over 2, 3 over 4, 7 over 8, 15 over 16. It's just the numerator minus 1. So this is 2 squared minus 1. That's 2 cubed minus 1. That's 2 to the 4th minus 1, etc. So, can you think of a general formula for this guy?
2 to the nth minus 1 over
2 to the n minus 1 all over 2 to the n. Right? That is a formula that tells me all the terms of the sequence of the partial sums. Now, what happens when I take the limit of that guy? Now, let's take the limit of Sn. That's just the limit of 2 to the n minus 1 over 2 to the n. Now, what's that?
Will be 1.
That's 1. So we did travel a mile. You add these all up, it adds up to 1. And not just because it makes sense. Yeah, if I travel half a mile, then a quarter mile, then an eighth of a mile. Yeah, eventually I'll travel a mile. That was the whole point of the whole ordeal. But mathematically, no. That infinite sum adds up to 1, mathematically. It actually makes sense that this thing adds up to 1. If I add up a bunch of things, starting at a half, going on forever, adding up things that look like 1 over 2 to the n, literally forever, what do they all add up to? They add up to 1. It converges to 1. A half plus a quarter plus an eighth plus 16 plus 1/32 plus 1/64 plus 1/28. And you keep going, they add up to 1. We traveled a mile. Okay, this is how we traveled a mile. Now, of course, this is kind of like learning derivatives from first principles, right? Like, oh, limit is included. Like, you don't want to do this all the time, right? That was like took a lot of brain power to get through that. So the idea is now, can we streamline this? Is there a nicer way to talk about what an infinite sum would add up to, if anything, at all, right? And unfortunately, the answer is no, so I guess we're done. No, of course there is, right? Now, of course, it also depends on the context. When we were in the Riemann sums context, the trick was to use the antiderivative to help us out. Now, in general, if we don't have a Riemann sum, the options available to us are a little bit more scattered. The answer is yes. So the next few sections of your textbook, the next 7 or 8 sections, goes down to doing this. Finding a very strategic, efficient way to compute infinite sums, a lot of times without us having to come up with a formula for the sequence of partial sums in the first place. Although, behind the scenes, the sequence idea is going to be an important idea. Do you want to do that first? first. Some important things. Let's talk about properties of series. So when it comes to the mathematics, what are things that you're allowed to do with series? In similar ways that you can deal with limits. So suppose the series of AN and the series of BN are convergent series. So here are two series that they add up to real numbers, each of them. And C is a constant. What kind of algebra do you expect to work out? Some general properties. One, if I have a series of a constant times a sequence, then you can actually factor that constant out. So that's a property you have, right? Which, of course, that makes a lot of sense because this side here is just you adding up a bunch of things that look like this. And then we know the distributive law says we can actually factor out a constant from all of that. Right? So it makes sense that that side equals this side. Here's another thing that you can do. So you can factor constants outside of series. That's going to be something that's important to know. If we want to algebraically manipulate something, that's going to be useful. Here's another thing. If you have a series generated by the sum of the terms of a sequence, right? So I take one sequence, I add it together, and then I add over all of that. Then I can actually add the sequences, the series separately. So the series of a sum is the sum of the series, right? That should make sense too. I mean, here, what this guy looks like is like your A1 plus B1, and then A2 plus B2, and then A3 plus B3, and then, but we could just group all the A's together, and then group all the B's together, and this is the same as that. It should be, right? So that actually works out. Like these seem very obvious, but obviously someone had to prove these. Because when you're adding up an infinite number of things, very strange things can happen. I'll mention something really strange that can happen when you're adding up an infinite number of things pretty soon. So that is, and that's basically it. That's kaput. That's it. So their series are not like limits. They don't have a lot of nice algebraic properties. So here's a common one that seems to always mess up. So let me specifically say that. Series do not distribute across products. So if I have the series of AN times BN, it is not the same as the series of AN times the series of BN. Very different things. You cannot actually distribute sigmas. Now, how can you see that? Well, if you take the sigma of AN BN, well, that's just A1 B1 plus A2 B2 plus A3 B3 plus going on forever. Whereas if you take the sigma of AN times the sigma of BN, what that means you're doing is you're taking all the A's added up together, and then you're multiplying that by all the B's added up together. Now, if you apply the distributive law correctly, you are going to get A1 times B1, yeah, but you're also going to get A1 times B2, and A1 times B3, and so on. And then you're going to get A2 times B1, and A2 times B2, and so on. And then you're going to get A3 times B1, and so on. This guy is actually larger than or equal to, in the case that some of these guys are zeros, than this guy. Right? So they're not the same. This guy is potentially a lot bigger than that guy. right? So they're not even the same. One can be like a larger infinity compared to the other guy, right? So sigmas do not distribute across products. They distribute across sums, and you can factor constants out. That's pretty much it. That's pretty much it for algebraic properties. So series, you have to deal with them very carefully. You can't just like limits and just like wantonly just throw them around. Oh yeah, distribute across the sum, distribute across the division, distribute, factor the constant out. No, you can do only these two things. Another thing that I want you to know about. So sometimes given a series, we want to consider some analogous series. Specifically, the series that you would get if I threw absolute values around all the terms. Right? So now, the series of an is of course a1 plus a2 plus a3. While the series of the absolute value of an just means the absolute value of a1 plus the absolute value of a2 plus the absolute value of a3 plus, okay? And so now, here's a definition. Is it a definition? Yes, it's a definition. Because I'm going to define a certain phrase that's going to be very important moving on. The idea of what's called absolute convergence. So, definitions. Consider the series an. We say the series converges absolutely. So that's a phrase that you're going to want to know. The series converges absolutely. I can make that phrase. If the series with absolute values converges. Right? So I have a series, I'm adding up an infinite number of things in a list. If I throw absolute values around each of those individual things and it still adds up to something meaningful, I say it converges absolutely. Right? We say an converges conditionally. So we have absolute convergence and we have conditional convergence. If an converges, but if I put absolute values around it, it does not converge. So when it comes to converging to some answer, there are two levels that we will consider. One, there's a convergence that happens when, even if I throw absolute values around the thing, it still converges. And there's a convergence that happens, well, if I leave things as is, it converges. But if I take absolute values around everybody, it does not converge. That's called converging conditionally. And we say, of course, an diverges if it neither converges.
Absolutely or conditionally?
Absolutely or conditionally. Thank you.
Do you know the blank copy of the quiz today?
I'll give you at the end of the class. So, remember what it means to converge. I can add up this list and it gives me a real number answer, right? Now, there are two levels to how this can happen. I can add up the list as is and it gives me a meaningful answer, or I can put absolute values around all the individuals and it still adds up and gives me a meaningful answer. In the latter case, I say it converges absolutely. If when I throw absolute values around everyone, it does not converge, but the original converge, I say it converges conditionally. If none of those two works, I say it now diverges. Now, this is very important because of a very weird behavior with adding an infinite number of things. And it's important for calculus specifically. This is important because of there's something called the rearrangement theorem. This blew my mind the first time I saw it. If anyone's even a little bit interested in math, they're going to find this very interesting. By the way, Riemann, the guy who came up with Riemann sums, came up with Riemann sums in his PhD thesis, right? 100 plus pages long thesis he wrote for his PhD. He invented the Riemann sums in that thesis. On one page of this thesis, he just kind of said this thing in passing. Oh, by the way, there's this thing called a rearrangement theorem, right? He was developing the Riemann sums, so you have to talk about summation and how they work and what does it mean to add up an infinite number of areas. And he's like, oh, by the way, when I was trying to figure out how to add up these infinite areas, I noticed this thing. One page of his thesis spoke about the rearrangement theorem. And he proved it and then moved on with his life. And it was something that said something quite crazy. But here's what it said, the rearrangement theorem. And then I'm going to tell you why it's important for us to know about these two kinds of convergences. Suppose AN converges conditionally and R is any real number. Any one. Pick your favorite real number. Pi, e squared over 9, 17.5, 6, 7, 8, 2, 9, 2, whatever. Any real number. Then the terms of AN may be rearranged so that they sum to R. In other words, if I have an infinite sum, it's possible to get a different answer if I just rearrange the order in which the things appear, right? Now, of course, this doesn't happen with finite sums. We have commutativity of addition. It turns out that does not work with infinite sums in general. It turns out you can have an infinite sum, you can rearrange the terms and end up with a different answer. More than that, you can end up with any answer you want. He pretty much showed that you could rearrange the terms to end up so that the sum converges to any real number you choose. We could also make it diverge by rearranging the terms. So, conditional convergence is a very fickle kind of convergence. It converges provided you don't do anything. Don't touch anything. Leave it as is. It'll work if you just leave it alone. Now, if you actually want to start doing math with series, that's a problem. Because now, if anything gets out of order or you mess anything up, the convergence gets messed up as well. But here's the cool thing about absolute convergence. If AN converges absolutely, to S, then all rearrangements will converge to S. In other words, commutativity of addition for infinite sums only works when you have an absolutely convergent infinite sum. If you have a conditionally convergent infinite sum, you can rearrange how you're adding things and get a different answer. You can even rearrange it in such a tricky way, you can get any answer on the real line that you want. You could also rearrange the terms that it doesn't converge all of a sudden. Right? You can get it to diverge to plus or minus infinity. You can get it to hop up and down between any two real numbers you want. Conditional convergence, you can rearrange order to get your sum to behave any way you want. If the terms converge absolutely though, no matter how you rearrange it, no matter what you try to do, no matter how you mess around with the order, it always will add up to the same thing. And that's going to be important. Consequences for calculus, which we're going to get to later. Now, this has consequences for lots of things, but it's going to have consequences for calculus. Eventually we're going to get to a point where we're going to want to use series to help us do integrals. Like what else, right? It's Calc 2, right? Now, if we want to compute like the series, the integral of a series, dn. So that is going to mean, okay, that's the integral of a1 plus a2 plus a3 forever, dn, right? You want to actually do that integral. We would like oftentimes to do this term by term. We would like to be able to integrate the a1 part, then integrate the a2 part, then integrate the a3 part, so on and so forth. But how do I know that's going to have any meaning whatsoever? If I can just rearrange the terms here and get a different answer, won't these integrals also give me a different answer? So here, what you end up with is a sum of something that looks like this. And it turns out that this step here, we're going to want to go from this step to that step to work out a lot of things. This step only works if if an converges absolutely. Now, don't worry about when we're going to use this. There's going to come a point where we're going to use this, where we're going to want to integrate a series. In order to get that done, we're going to want to integrate one term at a time. In order to make that switch from moving the integral sign from the left side to the right side, in order to actually make this switch, we're going to need absolute convergence. Because if we don't have it, this integral could be whatever. The integral is just not going to work out, right? We'd like to maintain the property that you can distribute the integrals, but we can't actually do that if it's conditionally convergent. So there are going to be times we're going to do this, and we're going to have to check first, is this an absolutely convergent thing? Because if it is, I know how to integrate it. If it's not, it has no integral effectively. It's not going to make any sense to actually do this. And that's due to the rearrangement here, something Riemann said in passing. It's a very surprising, very important theorem, and it kind of tells you how crazy infinite sums can get. Commutativity, don't take it for granted. It does not work in general. It only works if you have a finite number of things. So there'll come a point where we're going to do that a couple weeks from now. Maybe 2.5, 3 weeks from now, we're going to deal with this. And absolute convergence is going to be important. So a lot of times when we're going to talk about, does the series converge? We're going to care about, does it do it absolutely? Does it do it convergent, conditionally? Right, that's going to be important. Okay, what else do I want to say? So this section is just a lot of dumping new information, because series is a whole new topic, so a lot of introductions need to be made. So I spoke about that, I spoke about that, I spoke about that. I think that's it. Now, let's look into more efficient ways to tell if series converges. Efficient ways to tell if a series converges. Now, from this point on, it's going to be very similar to integration in the sense that I'm going to give you a bunch of techniques. I'm going to talk about when it's going to be convenient to apply which technique, and then you're going to use these techniques to tell me if a series converges or not. So we're going to do about 10 of them, right? So there are going to be 10 kinds of ways that you can check to see whether a series converges or not. And yeah, let's actually start off with we do this using what we call series convergence test. These guys will tell us if our series converge as long as the conditions for the test is fulfilled. We're going to do 10 of them, but I'm going to start the list at step 0 because this guy doesn't have a section to himself. He just kind of appears in one part of one of the sections. But it's decent enough that I actually want to point him out specifically. So we're going to do this guy and then n. It's called the telescoping series test. Telescoping series is one in which most terms in its sequence of partial sums cancel each other out. Making it easier to find the sum. So that's what a telescoping sum is. Let's actually just do an example. Look at this series. N goes from 1 to infinity of 1 over n squared plus n. So I have a sequence. The terms are given by 1 over n squared plus n. Then I start adding up all those numbers. So now you realize that this adds up to plug in 1, you get a half. Plug in 2, 6. Plug in 3. Get 12 plus 1, right? Does that actually add up to anything? Turns out it does. That actually adds up to something meaningful. It doesn't go off to infinity. But the idea is, I want to set up some partial sums, a sequence of partial sums, and have them kill each other off, right? Ideas on how to get that done. How can I turn this into competing factions? Right now it's one fraction.
Could you divide by n?
You can't divide by n, you change the values. Yeah.
Can we multiply by -1 to the n power?
What?
Can we multiply by -1 to the n power so you have an alternating signs?
Nope. You change the value when you do that. I mean, look at the goal. We want people to kill each other. So maybe having several things instead of one thing might allow the individual things to kill each other. Yeah.
One factor the n and then separate.
How?
Like a factor in the n is going to be n times n plus 1, and then you can spread it out into 1 over n times. Basically,
So partial fractions was the answer. Partial fractions, now we're going to look at this. So yeah, you still have to remember that. You can actually take this guy, write it as that, and also write it as just two separate fractions. What are the coefficients? 1 and -1. -1 seems very beneficial. So now, remember what convergence means. Recall. A series adding up to s means that the series is the limit of a sequence of partial sums, right? So what we're going to do is we're going to find the limit of the partial sums of this series And you're going to notice because of this negative sign, a lot of these guys are going to actually cancel each other out. They're going to kill each other. So, this guy, n goes from 1 to infinity. 1 over n squared plus n. What we're going to do is we're going to think of this as the limit, as say, I'm adding up the first n terms, and go from 1 up to big N of this guy. Right? This is equal to that by partial fractions, and now I just want to add up the first n terms and see what happens to it. Notice that this is going to be the limit as n approaches infinity of, let's just write out a few terms, see what this looks like. If I plug in n equals 1, I get 1 minus a half. Plug in n equals 2, I get a half minus a third. Plug in n equals 3, I get a third minus a fourth. Plug in n equals 4, I get a fourth minus a fifth. I think at this point you're getting the idea. Plus dot, 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 dot. Okay, so this was the n equals 1 term, the n equals 2 term, n equals 3, n equals 4. Now, how many terms do you have to write out? Enough for you to see a pattern, but I think by now you should be spotting a pattern. Let's write down the last few terms. N equals big N minus 2. N equals big N minus 1. And n equals big N. That would be where this partial sum terminates. So this part, if I use that formula, this is going to look like 1 over n minus 2 minus 1 over n minus 1. Plus, this part would be like 1 over n minus 1 minus 1 over n. Plus, this part would be like 1 over n minus 1 over n plus 1. Okay, so what do you notice now? A lot of guys actually cancel out. In fact, most guys cancel out. Minus a half plus a half. Minus a third plus a third. Minus a fourth plus a fourth. Minus a fifth. The next term is actually going to be plus a fifth. That's going to cancel out. Going all the way down to the end. This guy's going to actually get canceled by the guy just before this. So we know that that's all going to cancel. This cancels that. This cancels that. So pretty much everyone cancels each other out except the first and the last guy. Now it's not always the first and the last guy. There might be several terms, but for this particular example, if I write out the sequence of partial sums, I can express it in a way that everyone cancels out except the first and the last guy. Now, by definition of what it means to converge, all I need to do is find the limit of that guy as n approaches infinity, which is 1. So this is another thing that adds up to 1. This equals 1. So you take a half plus a 6 plus a 12. It adds up to 1. And I took advantage of noticing that this was a telescoping series. Now, I'm going to talk about how you recognize that something is a telescoping series. Why would you try this in the first place versus trying something else? But that's going to continue next time. So right now we're going to be in series convergence test mode. We're going to do a bunch of tests and setup. Does the sign of series I'm looking at, does it actually converge to something meaningful? How do I know? How would I figure it out? That's what we're going to do. And then we're going to use that stuff. So we will continue with that next time.
Thank you.